start with, we'll wait for 1 more minute and we'll start. My screen is visible, right?
No, sir.
No, sir.
Now?
Yes, sir.
Fantastic. I'll start recording and we'll go with the clash. In the previous class, we had seen the conceptual ideas behind how exactly fading occurs, what are all the different types of analysis that we are going to have, and what is the basic necessity for going for a diversity scheme, and how well it can be combined in such a way that we get a better performance in wireless communication systems. Now, the basic crux of that wireless communication system, whatever we had discussed in the earlier class, was about maintaining one or more antennas to get either transmit or receive diversity, and based on the diversity, we'll get better performance. That's a theoretical concept. Now, how do we get that better performance? That is what we are going to discuss in this class. Now, first I'll start with the basic analogy of one transmit and many number of receive antennas. Now, this is my transmit antenna, one transmit antenna, and let's say I have one receive, second receive, third receive antenna, so on and so forth. Okay, it may go up to NR number of receive antennas. Now, what I have to do here is the same piece of information has been conveyed from the transmitting antenna and it will be received at the receiver. That is what we have understood. Here, this is available here, this is available here also. Now, in case of our selection combining, let's say we'll talk about selecting and combining. First diversity technique is select and combine, or it is also called as selection combining. First diversity technique. Okay, selection combining. Now, in this selection combining technique, what happens is, now I have a combiner over here, and I'll get one output, gamma R, gamma summation, or gamma T, or whatever equation you want, you use it. Different textbooks follow different notation. Anything you can use, not a problem. Okay, as long as you understand what is this. Okay. Now here, I have received one signal. Let's say I have received some signal. Let's say the SNR of the signal will be somewhere like this. I have received another copy of the same signal and the SNR is somewhere like this. Okay. Somewhere like this. And I have received one more signal here and the SNR copy is somewhere something like this. Now, what I call this as 0101110100, something information has been transmitted here. Some information has been transmitted from the transmitter and you are detecting it as an analog signal here, and it has to be digitally converted and you will get a combined signal in terms of SNR. Now, whatever happens here is analog, right? So the thing is radiated and received. Now the crux of the problem lies here. Now 00 you have transmitted, 01 you have transmitted, 11 and 01 has been transmitted. Now this is a complex symbol. This is also a complex symbol. This is also a complex symbol. This is also a complex symbol. You don't have to group it in terms of 2. You can group it in terms of 3 or 4 in powers of 2, whatever. Now, important aspect is 00 has been, if you are using a particular constellation point, from M, let's say QPSK, it will be a complex point and it will be radiated as a complex vector over the air. Now similarly 0, 1 is another constellation point, 1, 1 is another constellation point, so on and so forth. Now what is happening here? Now you are transmitting a symbol, you are receiving a symbol. This is typically represented as X or S. The symbol which you are going to transmit is generally represented as X or S. Okay. Now, whatever is happening here is because of the air medium, this is called the channel H. Now, H is generally defined as NR cross NT matrix because you have more than one receiver here. So it will be represented in terms of 3 cross. Now here we have 3 cross 1. 1 transmit antenna, 3 receive antenna. You can write it in terms of NT cross NR also, but that becomes a column vector. Then you have to transpose it. That's all. Nothing more, nothing less. Now, whatever you are going to receive here, it is the combination of H into X or H into S. H into S. Now remember, in the last class we had discussed the if all these receive antennas are separated by lambda by 2 distance, and the channel becomes different. Channel becomes different, and it won't apply for our indoor scenario. It applies only for outdoor propagation scenario. This is well understood. Now, in general terms, Y is called the received vector, NT cross 1 received vector. That is equal to the combination of H into S or X, whatever, H into S plus the noise in the system. Now, if you have more number of H, means more number of branches, H will be H1, H2, H3. But this S would remain the same. This S would remain the same. H1S plus N1, H2S plus N2, H3S plus N3, so on and so forth. Now I'll write it as HIS, okay, and then NI. Okay, this could be YI, or here also you can write. Okay, now Y is the received vector, H is the channel, S is the symbol that is radiated, S or X, N is the additive white Gaussian noise that has been added to the system. Okay, this is the fundamental equation that you can think of. Y is equal to Hx plus N or Y is equal to Hs plus N. Now, let's take the same example here. Now, let's go and understand what is selection combining. In selection combining, something has been transmitted. Okay, now I have receivers. Okay, I have receivers here at the receiving end. I have receivers 1, 2, 3, so on and so forth. Now I'll have a commutator switch or a switch here over here which select the best possible signal strength here. Best possible signal strength means if the signal strength of this branch is high, I will select this. If the signal strength of the second branch is high, I'll select this. I'll select this if this is good. And then I will combine this and I will transmit. Now, you have to understand one thing. You have to set a threshold. What is the threshold that you are going to set in order to choose this SNR is good, or this SNR is good, or this SNR is good? Now, in order to do that, I have to write it in terms of a simple analogy, that is with respect to time, and I have somewhere like gamma threshold or SNR threshold or gamma sigma, whatever you want you call it. Okay, I'll set a threshold over here. Now, once I set the threshold, whatever is on the y-axis is gamma, whatever is on the x-axis will be my t. Now, I will take first branch. Let's say I will take the first branch. First branch, if I take, I'll calculate the SNR. I'll find out what is happening with that. Let's say the signal is like this. Okay, let's assume this is branch 1. Now black is branch 1. Black is branch 1. Okay. Now my SNR is like this. The signal received at the receiver looks like this. Okay. and I have a commutator switch or a switch. Let's assume this is a switch, and the switch will take the respective signal. I'll take another branch. I'll take another branch because the same copy of the signal that has been transmitted, only one transmitter I have somewhere, it will start at this point only, and I may have a different SNR like this. Who knows? I may have a different SNR. And this gray color is, let's say 2. Okay. Now, next, I will take another branch. I'll take another branch. Now 3 branches I have taken. This blue is 3. Now what is happening here? Now how do you understand this? Now if I say the switch takes the highest SNR, okay, this also, now you have to divide this into number of time slots. Let's say I will divide this here. Oh, we will take a new color over here. Oh, sorry. Okay, I'll take a new color over here, and I will take this as time t1. I'll take this as time t2, just to understand, that's all. Time t3, so on and so forth. Now what is happening here? I have set the gamma threshold, that is the SNR threshold, so that minimum SNR that is required in order to have a successful reproduction of the signal is my gamma threshold or gamma sigma or capital gamma, whatever it is. Now here, this threshold has to be met in order to keep the signal active. Now what I do is, based on the selection combining, selection combining is nothing but select the maximum SNR. At T1, I'll select this. Look at this. Are you all with me? Here I will select this. Now the moment I reach this point, SNR of the black one goes very low. SNR of the black one goes very low. I'll not take that line because maximum SNR has to be taken into consideration. So I'll choose this line. Now, till this point, there is no other alternative. I have to choose this line only because there are no other branches which will give you maximum SNR as that of this branch. So I'll follow this path. Again, I'll follow this path. Now look at this. The blue one takes a shift to the lower SNR axis. Now, what do I have? What best I have? I have a gray one. I'll go to the gray one, and then the gray one will shift to the lower SNR. What do I have? I have a black one. I'll take this black one, so on and so forth. And I'll take this, so on and so forth. Like this means properly you have to write, okay, like this. 1 second. I will take this as the signal, higher SNR, signal strength, higher SNR. This is also higher SNR. This is also higher SNR. And here I don't have any other value. I have to go below SNR here, and then I'll reach this signal, so on and so forth. Again, it will reach somewhere like this, Okay. Now what is happening here? Yeah.
So what will happen if there's a delay in one of the signals? Suppose black is delayed.
I'll come back to that.
Okay. Thanks, sir.
Now here, his question is delay. Okay. Delay. How to address the delay? I'll come back to that. Now look at this. Now what is happening here? The peaks have been reinforced. The peaks have been followed. The level crossing rates at the SNRS, at the threshold SNR, has changed. Now if you follow the black one, what happens? The SNR will go below the threshold level. So the level crossing rates have been identified as the threshold, and you are being moved across the SNR based on the highest signal. Now, average of the signal has been changed. That is the important aspect of your selection combining. Average of the signal has been changed compared to individual branches. Average of the signal has been changed, isn't it so? Now, the next important aspect of this is what could be the range. Now look at this. At time instant t1, there will be no time instant, whatever it has been represented like this here. This is for the sake of understanding, that comes overall through the combiner. For a split second, 10,000 bits will occur at the combiner. Now what is happening at the time t1? This is branch 1. 1 is selected. Next, again 1 is selected. Again 1 is selected across this branch. 1 is selected, and again 3 is selected here. Branch 1 and 3 has been selected. Is it possible to select like that? Yes, it is possible. Okay. Now, the next step is, what is the dynamic range of the signal? Dynamic range of each signal can be quantified as what is the peak and what is the lowest value. Now, the lowest value could be this and the highest value could be this. So the dynamic range of this black signal, dynamic range of each signal has to be quantified. Maybe similar, maybe very less, or maybe large. It depends on how the SNR is varied. Now you have to compare the dynamic range of the final signal, that is the pink one, whatever I have marked. Okay, final signal. Okay, final signal with the individual signal. What has happened? Dynamic range of the combined signal has reduced. Means the SNR level will not go below this threshold SNR or the threshold value at all times. If all the, just understand this, just try to understand this concept very carefully. If all the subsequent branches goes below the threshold SNR, then only in our case our SNR goes low. Otherwise SNR, most of the times the SNR is very high. Most of the times SNR is very high. Can this be implemented? There are a lot of lacunas. There are a lot of complexity issues also. Okay, I'll come back to that complexity issue. Now, come back to this question. Now, the question being asked is, what happens if there is a delay? If there is a delay signal, no matter what, if there is a delay, let's say the signal, instead of, let's consider a black signal, I will replace the black signal with a green one. Now, instead of starting at this point, the signal has started, let's say here. And if it follows the same path, like this, if it follows the same black line path, okay, then automatically your green signal, whatever you have a delay, it will be rejected because you have a subsequent amount of delay that has existed in the system. And then you are just going with the selection of the highest peak SNR. There is one more possibility. What if this delay signal has a maximum SNR at different time intervals? Then you take it. Now, if you have something like this, you just take the peak of that signal. Now, there comes another confusion. What happens if the delayed SNR, if you take it into consideration, bits might be lost? If you have transmitted 1011, something like that, because of the inherent delay produced by this, if there is a delay, the 00 could be lost. Yes, there is that problem. Now, what you have to do is, in order to understand this, you have to understand what is the maximum BER. The average out BER or averaged SNR signal only you are taking. If the signal is lost at particular time instant, at particular T1, if the signal or the symbol is lost, that cannot be recovered. That is said to be lost. That comes under your error. That comes as an error. Okay. Now, is this the optimized system? Is this the optimized way of handling the situation? No, definitely not. Then what could be the optimized way? We will discuss that. Now, the delay part, when there is a delay, because of the delay, signal might shift. It doesn't matter if the signal is shifted. Based on the average SNR above the threshold, then only it will be selected. Otherwise, there is no consideration of the delay. If the signal or the symbols are said to be lost, it is lost. That's all. Now 00 has one signature print, 10 has another signature print, 11 has another signature print. It doesn't matter. It doesn't matter for the combiner. Combiner sets a threshold and it takes the maximum value or maximum content of the signal. Anything else? Okay. Now look at the pink one. What is happening with the pink one? Now the pink one, the pink line, if you follow the pink line, what is happening at the pink line is received signal strength, or it is also called RSSI, received signal strength indication. The fluctuation of the received signal strength is very less. This is very less. This is very less because You have somewhere like this and this and this, so on and so forth. Compared to original branch, compared to the original branch, the fluctuation of the signal strength is very less. That is the signal y, whatever it has been received, y square, the fluctuation of this pink line is very less compared to the individual signal or the signal which goes below the SNR threshold. So peak may be similar, but lower range has reduced significantly. This lower range, lower threshold ranges have been reduced significantly. So the average has shifted and the variability of the signal has been changed. That is the concept behind this selection combining. Okay. Next, after this, you have one more criteria, how to understand this mathematically. How do you understand this mathematically? Okay, now how do you understand this mathematically? The first question arises in our mind is, what is the impact of your digital communication or wireless communication system if you change the average and variability parameter? Now you have changed the average and some variability parameters you have changed. Variability parameters you have increased or decreased. What is the impact on the system? What is the performance analysis? What is the impact of the system? That you have to understand. Now we'll go to the core mathematical part. Consider the signal. Okay, consider the signal that is received at the receiver. That is, I'll write it in terms of yi, that is equal to h. H is the channel matrix. Hi, I will write it as hi into the signal s plus noise, additive wide Gaussian noise, ni. Now I is what? I is equal to 1, 2, 3, 4 up to say L number of branches or MR number of branches. Received branch. Received branch. Now Y conjugate, the argument which maximizes the H. So I will write it as y, it is a complex conjugate, it is a complex number because your a plus bi, x plus iy, or the symbol 1 plus ij, 1 plus I theta, whatever you are sending is a complex symbol, hi conjugate into s plus ni conjugate. Okay, the representation. Now what is this I conjugate? I conjugate is equal to argument max of this mod h square. What do you mean by that? You mean argument which maximizes this hi square over all the branches. Now come back to this figure. What am I doing? Argument which maximizes this I over all the branches. That is the physical insight. Okay. Hi square, that is the argument which maximizes hi, the channel matrix, over all possible I. Select that branch based on the different values of h. Select that branch which is maximum, that is argument max. Okay. Now yi is the you have to remember this, yi is the received signal. I'll write it as received signal in the ith branch, Now what does it mean? For all values of I is equal to 1 to mr, what is yi? That you have calculated, that's all. Now s or x, generally it is x or s, is the transmitted symbol, that is the transmitted symbol. And then hi into x or hi into s is the hi into s or hi into x is the multipath behavior of the channel. That's all. Multipath behavior of the channel. For the same symbol, that is this s or x that has been radiated. Ni, you know, Ni is the additive wide IID Gaussian noise. IID, independent and identically distributed additive wide Gaussian noise. It is actually circularly symmetric. Okay, circularly symmetric and which has complex IID. Okay. Now, if you want to understand what is happening at each branch SNR you have to take in terms of expectation and the signal strength over noise strength. Now each branch experiences the fading SNR, each branch SNR, that is equal to gamma I, okay, that is equal to hi square mod into expectation of S that has been transmitted with respect to expectation of IID Gaussian noise that is received at the receiver. This is expectation square, that is I, if you write I is equal to 1, 2, 3, so on and so forth up to MR. Okay, hi into ES square divided by expectation of S square divided by expectation of N. Now what is this expectation of Ni? That is, you have studied in your digital communication system. How do you write? That is your sigma N square. Expectation of S is the symbol, that is the power that is radiated. Okay, that is your PS or P or PT or whatever. With respect to symbol I'm writing, that is why I'm writing it as PS. Now expectation of S square divided by expectation of the additive white Gaussian noise is equal to what? It is always called as gamma bar or capital gamma or gamma bar, that is equal to your PS divided by the sigma Ni square or sigma Ni of the individual branch. What is happening here? Now for a Rayleigh distribution, you have what is the expectation of EHI? For a Rayleigh distribution, expectation of hi square is equal to 1, EHI is equal to 0. Now if you take the probability density function PDF of Rayleigh, if you take the PDF of Rayleigh, what happens is PDF, let us consider the channel as Rayleigh. Let's say NLOS as well as LOS component you have, dominant NLOS you have compared to LOS. Now the channel as Rayleigh distributed, or this exponential term will come into picture. Hi square becomes, this channel matrix can be modeled as hi square is equal to PDF of SNR in terms of Rayleigh. If I write Rayleigh distribution, this will be equal to 1 by capital gamma into e to the power of minus gamma I divided by capital gamma. This is also equivalent to 1 by gamma bar. 90% of the books will follow this architecture, that is small gamma bar, and you can write whatever you want. You can write in terms of F also, F gamma of gamma also. This is also from CDF. You take the d by d gamma of this, you will get PDF. Take the CDF and get the PDF. Differentiate the CDF, you will get the PDF. Now what I am trying to explain here, this is my PDF for a Rayleigh distributed signal, and H has been distributed according to this function for all gamma I bar greater than or equal to 0. 1 by gamma bar into e to the power of minus gamma I by gamma r. Gamma bar is the PDF. Now considering the expectation of gamma I, that is equal to gamma bar or capital gamma, that is expectation of channel and expectation of SNR with respect to the channel what you are going to deal. Now what is that? Now if you talk about the SNR in terms of expectation of channel and expectation of SNR, I will write it as gamma I. Expectation of gamma I is equal to expectation of the channel, that is my mod of hi square into gamma bar. That is my gamma bar. So that will be the signal strength based on the signature of the channel. Okay, and I will have one expectation of hi square for Rayleigh fading. This becomes equal to 1. What I'll get is expectation of gamma I is equal to gamma bar for a Rayleigh distributed function. Now you can also calculate the outage probability based on this. E of gamma I is equal to gamma bar. It doesn't make any sense. It doesn't make any sense until unless if we don't understand what is this, you don't understand anything. Now for that you need to understand the Rayleigh distribution, what you have studied in chapter 4, 5, whatever, 5, 6 also. So what is the probability that gamma I that I am going to receive, this gamma I is less than the gamma threshold? What is the probability that gamma I, whatever I am going to receive, is less than the gamma threshold, lesser than this gamma threshold value? So the probability that gamma I is less than the gamma threshold can be calculated as integration over 0 to threshold. 0 to threshold you integrate, you will get the PDF. If you integrate that, you will get the outage probability. As simple as that. It won't look as simple as that, but you have to do it. Probability of gamma I less than equal to gamma threshold is equal to 0 to gamma threshold, okay, into Pi gamma I into d gamma I. Okay, that is P out. If you want to calculate P out, that is equal to 0 to gamma threshold into, this is, what is that? The based on the CDF, I can write this as 1 by, oh sorry, based on PDF, I can write this as 1 by gamma bar that I had it written already. 1 by gamma bar e to the power of this one, okay, into e to the power minus gamma I by e to the power of minus gamma I by gamma bar into d gamma I. Integrate this, you will get 1 minus of e to the power of minus gamma threshold divided by gamma bar. Okay, this is the probability that signal falls below the threshold. This gamma threshold is because applying the limit gamma threshold minus 0, you will get 1 minus e to the power of minus gamma threshold divided by gamma bar. So this is the probability that signal falls below threshold. This is the probability that signal falls below threshold. Falls below threshold. Now, what have you understood? Now we know this channel is a Rayleigh channel. The expectation of Hi square is equal to 1. EHI becomes equal to 0. Expectation of a Rayleigh fading channel, expectation of Hi square, mod Hi square is equal to 1. Now what is happening with the Rayleigh channel? This is one transmit and many number of receive antennas. I have transmitted a symbol or a signal and it has undergone Rayleigh fading. Now how do you find the CDF and PDF? The basic concept of basic way of finding the CDF and PDF is pretty simple. Now you have a transmitter over here, you have a receiver over here. Now let's say the distance of communication is 50 kilometers. Let's say you send pilot symbols from transmitter to receiver. Send back what you have received at the receiver through a paging channel or whatever channel you have. So known sequence, this is the least square estimation, known sequence of 100 ones and 100 zeros have been communicated, let's say from the transmitter to receiver. Just try to understand this point. Okay, now I have a transmitter, I have a receiver, so distance of separation is NLOS and let's say it's about 50 kilometers. First, pilot symbols have been transmitted in order to estimate the channel. Whatever mass functions, the digital mass probability mass functions that you are going to receive in discrete domain, okay, based on that, if you fit it to a curve, okay, you will get a distribution. That is your CDF. The first derivative of the CDF will be your PDF. How do you estimate the channel? Estimate the channel based on the known sequence of symbols. Known sequence of symbols have been transmitted, it will follow a distribution. In indoor, it follows another distribution. In outdoor, it follows another distribution because of the variation of the channel. So once you understand this, CDF and PDF, you will come to know. Once you know the CDF and PDF, for a relay channel, you can calculate the outage probability. Outage probability is nothing but 1 minus e to the power minus gamma threshold by gamma bar for your relay channel. That is, this is the probability that the signal falls below threshold. For any one branch, if you want to calculate, for a single branch, now for a single branch, single or any one branch, if you want to follow what is happening now, that P out or PO or P out, okay, outage probability is 1 minus of e to the power of minus gamma threshold divided by gamma bar, and this is 1 minus P naught is equal to e to the power of minus gamma TH. Just a small modification, that's all. You bring it down to the left side and take the log. That's all. Natural log of 1 minus P naught is equal to minus gamma TH divided by gamma bar. And hence change the sign and get in terms of gamma bar. I want it in terms of this. So I will take it as 10 log 10 of gamma bar minus 10 log 10 gamma threshold, that is equal to minus 10 log 10 log 10 of natural log of 1 by 1 minus P naught. Now, whatever I am getting over here is called the fade margin. Fading margin. Now, this term, what I'm going to get is the gamma bar is the average SNR. This is my average SNR, and this gamma TH is the threshold. Now, I have understood two things out of this equation. For single branch, minus 10 log 10 natural log 1 by 1 minus P naught I will get, and I'll come to know what is the fade margin. If you go back to this, what is the fade margin here? What is the fade margin? And whatever I'll get here is the fade margin. Okay, signal, fade margin I know, threshold I know. From that, I'll calculate what is the outage probability expression for a given channel. Now, outage probability expression in general, it has been designed in such a way that you will get what is happening with one branch. Now, the branch has not been combined yet. The branch has not been combined yet. Now, all M branches independently faded. All branches have been independently faded, IID, independent and identically distributed, and the fading will be different. So what happens? Probability of gamma 1, gamma 2, so on and so forth, gamma MR up to MRth receiver, you need to find out which is less than the gamma threshold. So this can be written as the product of I is equal to 1 to M. 1 to MR also you can write probability of gamma I less than equal to gamma threshold. Now this probability is equal to what? This is equal to the same equation, whatever I have written over here, 1 minus e to the power of minus gamma threshold divided by gamma bar. This is for 1. And if you have M number of branches or MR number of branches, you will have 1 minus e to the power of minus gamma threshold divided by gamma bar whole to the power of M. So the probability, outage probability of SC, okay, that is selection combining of gamma threshold. Calculate PDF for this. Gamma I greater than equal to gamma bar, 1 minus of this will be probability of coverage. So this will be equivalent to 1 minus of e to the power of minus gamma threshold divided by gamma bar whole to the power of M. For M branches, for M branch diversity. Now, how did we get this? We got this because we knew what is the CDF. From CDF, we have taken the first derivative. From the first derivative, we know what is PDF. Now, for the PDF, we calculated this outage probability, integrate between 0 to gamma threshold. We came to know the outage probability. Because probability of gamma 1, gamma 2, gamma 3 up to gamma R or gamma MR is less than gamma threshold can be written as I equal to 1 to MR. Probability of gamma I, which is less than gamma threshold, it is finally written as 1 minus e to the power of minus gamma threshold by gamma whole to the power of M, because you have M branch diversity. Now, what is the probability of coverage then? What is the probability of coverage? The probability of coverage is nothing but 1 minus P, 1 minus probability of SC, that is outage probability of your selection combining. So if you want to calculate the probability of coverage, it is simply probability, what is the probability of gamma I greater than gamma? That is 1 minus of PSC. Okay, outage SC with respect to gamma. That is equal to what? 1 minus of 1 minus e to the power of minus gamma by gamma bar whole to the power of M. Okay, from CDF differentiate, you will get the PDF. So for this, if you differentiate, Pm of gamma is equal to first derivative. First derivative is m into 1 minus e to the power of minus gamma divided by gamma bar whole to the power of m minus 1 into gamma by gamma bar into e to the power of minus gamma by gamma bar. So mean SNR can be obtained by integrating over 0 to infinity so that you will get a final equation. In books, it has been given as the final equation as something like you integrate in between 0 to infinity P gamma m of SC of gamma into d gamma. That is little tricky, but I'll show you how to do it. Okay, that is equal to gamma MSC or gamma m of SC bar is equal to gamma bar into summation I is equal to 1 to m 1 by I. This is the final equation that they have given. How to arrive at this? No book will tell you how to arrive at this. For this you need a little bit of binomial expansion and infinite series, P series, so on and so forth. If you are interested, you just learn this. I'll try to write how it can be done. Now, first I'll take mean SNR can be obtained in between 0 to infinity. But you have to remember this equation and the method also, because you will be deriving all these things. Okay. 0 to infinity P gamma of SC into P gamma of SC, that is gamma into D gamma. Now, what is my probability of probability density function? My probability density function is 0 to infinity gamma m divided by gamma bar. What is that? What is that I got? M into 1 minus, I'll take this gamma somewhere here. Okay. Okay. 1 second. I'll write it and show you. Gamma m, this gamma I'll take it out. M gamma, this gamma, whatever this gamma I have, I'll take it out. M gamma divided by gamma bar. You will come to know. Okay. Okay. Gamma m by gamma bar into 1 minus e to the power of minus gamma by gamma bar equal to the power of m minus 1. This is the first derivative of the CDF into e to the power of minus gamma by gamma bar into d gamma. This I have to integrate in between 0 to infinity. Once I had derived this equation, probably you just follow. I'll try, because this is very important. Numerical computation, numerical analysis is also required in order to get this equation. To get this equation, gamma m bar c, this is gamma sc is equal to gamma bar into I equal to 1 to m 1 by I. It's a little tricky. Okay, first I will take this out. M by gamma bar. M by gamma bar, I'll take it out. 0 to infinity gamma into 1 minus e to the power of minus gamma divided by gamma bar into m minus 1 into e to the power of minus gamma by gamma bar into d gamma. So you know binomial theorem. Binomial series also you know. Binomial theorem. First PUC. Okay, binomial theorem. For the sake of simplicity, I'll write it over here. A plus b whole to the power of n is equal to summation I is equal to. How do I arrive at this? Because I came to know this because the intuition says I equal to 1 to m. Whatever integration I am doing here in between 0 to infinity, I am representing it in terms of increasing SNR. Increasing SNR is summation of all these terms. So summation can be brought by some numerical calculations only. So I is equal to 0 to n, correct? I is equal to 0 to n choose I into a to the power of n minus I, b to the power of I. You can change the order of summation and you can change the powers also, that you know. This is very important formula. Apply the same thing over here. Now I'll write it as equation A and equation B. From B, apply the same thing to A. If you apply, what happens? This is equal to m by gamma bar is outside 0 to infinity. I'll write gamma in terms of summation. I'll write I is equal to 0 to m minus 1 and n choose I becomes m minus 1 choose I, because it is m over here, okay, into minus 1 to the power of I. We have one more 1 minus e to the power of minus gamma by gamma bar term. I will write it in terms of e to the power of minus gamma by gamma bar whole to the power of I into e to the power of minus gamma by gamma bar into d gamma. Okay, then m by gamma bar is equal to summation I is equal to 0 to m minus 1 minus 1 to the power of I. I will take m minus 1, choose I will take out and integrate in between 0 to infinity, because I have to observe these terms, e to the power of minus gamma by gamma bar into e to the power of minus gamma by gamma bar into d gamma. So this term becomes what? Gamma into e to the power of minus I plus 1 gamma divided by gamma bar into d gamma. You have to play around it, that's all. But provided you should know this binomial expansion. 0 to infinity, there is one formula, that is gamma or e to the power of minus c gamma into d gamma is 1 by c square. 0 to infinity a into e to the power of minus ca into dA is 1 by c square. So apply this is c. Apply this c. So the same thing here, you have to apply here. And what happens is this is equal to m by gamma bar. M by gamma bar into summation I is equal to 0 to m minus 1 minus 1 to the power of I, or whatever, m minus 1 choose I into gamma bar divided by I plus 1 whole square. Isn't it so? Now this gamma bar and this gamma bar get cancelled. You are left out with an equation gamma into m summation I is equal to 0 to m minus 1 into minus 1 to the power of I. What was that? What was that I have written? Gamma bar. Okay. Now this becomes m minus 1 was there. M minus 1 choose I. Okay. M minus 1 choose I. That is m minus 1 choose I have divided by that gamma bar has cancelled, that gamma square, one gamma square has got cancelled. I have written the other gamma here. Remember here, this is the 1 by c square. Okay, this becomes what? Gamma square, actually this gamma square term. Okay. So this becomes m minus 1 choose into I plus 1 whole square. So what is that? This implies summation I is equal to 0 to m minus 1 minus 1 to the power of I into m minus 1 choose I divided by I plus 1 whole square. This is equal to what? You substitute I equal to 1, 2, 3, so on and so forth. It will boil down to I is equal to 1 to m, 1 plus 1 by 2 plus 1 by 3, so on and so forth. This is equal to summation I is equal to 1 to m, 1 by I. This is what I have got, no? Gamma bar into 1 by I. Gamma bar into 1 by I. So the same term, this gamma bar is here, the whole term whatever I have here. The whole term whatever I have here can be represented in terms of this. So this term whatever I have here, gamma SC, that is, this is the total SNR obtained by integrating 0 to infinity. So gamma bar SC is equal to gamma bar into I is equal to 1 to m, 1 by I. Increasing SNR is observed in terms of 1 plus 1 by 2 plus 1 by 3, so on and so forth. This is how you got 1 by I. So just you try to do it 1 or 2 times, you will get the answer. Now what is the physical interpretation of all these things? Why you have to do all these things? See, the physical interpretation is, now whatever you have done with respect to T and with respect to gamma threshold or whatever you have done, you have minimized this SNR, which is going abruptly below this threshold value. You have minimized this. So what does it mean? In order to calculate what is happening with respect to the SNR, the probability, outage probability and the probability of coverage, how it increases is with respect to what is the probability that you have got. Now, by seeing this equation, 1 minus, yeah, by looking at this equation, when the order of m increases, means when there are many number of branches, what happens here? What happens here? Automatically, the fluctuation above SNR will be very high and the signal will be retained properly so that a suitable combiner will combine all these signals. But is it really practical? Is it really practical? By doing like this, is it really practical? Can we go ahead with this solution? You can go ahead with this solution, but what is the number of switching transients are happening? 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. So look at the switching transients. The switching transients are something like, it's hectic switching transients are happening. Now, how do you avoid that? In order to avoid that switching transient, there's a low complexity technique which is used as switch and stay, or switch and branch combining, switch with the beam combining. Look at this. Now, this is my signal. I'll take only 2 or 3 for the sake of simplicity. Okay. I'll take something like this, and I'll take something like this, and I'll set a threshold here. Now, what I'll do is I will go with this. First, I don't have any other option. I will start with this. I'll start with this and I'll move to this point. Now, instead of switching it to green, like switch, that is your selection combining, I'll follow this here. Since I follow this one here, I don't have any switching transient which is there here. Now I need to switch back to higher SNR here only. Instead of switching at this, I have to switch at this. What does it mean? It means if the switching is happening inside the or greater than the threshold, I will stay. The switching I'm avoiding at the greater threshold. Are you all with me? Switch and beam, switching and staying here. Now I have switched here, but I'm staying at the higher SNR. Now, if I follow at this point, if I come to this point, I have followed this branch because there is no other alternative branch. Though in selection combining, I might have gone with this because of the highest SNR, highest possible SNR. Here, what I'm doing is I don't have any other SNR. I'll have to come back to this lower SNR and I'll have to switch over here. Now, then instead of switching to the green, I'll follow this because this is at higher SNR. Means switching and staying is nothing but switch at higher SNR thresholds. If the threshold is not going below, and if there is another switch comes in between, which is higher than the highest threshold, which is already available, don't switch unnecessarily. Now I don't have any other option. I have to switch here. I have to follow this path and I have to go with this path. And again, instead of switching over here, I'll follow this path. And here I have another path here, so I'll switch here. This way, I have maintained maximum possible SNR. Maximum possible SNR. Now, what does it mean? It means I have stayed for some amount of time if my signal strength, as and when my signal strength does not go below this threshold value of SNR. Now, if there is no other alternative for the signal, then it has to go through, or if there is a connection, or if there is a switch, or if there is a SNR higher than this point, I can switch it like this, but that is an improper switching. Improper switching. This is switch and stay combining. In switch and stay combining, unnecessary fluctuations like selection combining is avoided. More number of switching transients or the switching transients have been avoided. So the signal looks flat or little smooth compared to your selection combining. This is a low complexity suboptimal alternative to your selection combining. Selection combining may not be optimal, but if you consider selection combining as an optimal parameter or optimal detection scheme, and this becomes this switching and staying combining method becomes, or switching beam combining technique becomes your low complexity suboptimal. If you are getting a performance improvement of about 3 dB here, you will get approximately half of it, 1.5 dB, because this may reach lesser gamma threshold values. It may even go to lower SNR. So this is switch beam or switching and stay combining. Switching and stay combining. Okay. Now there is for this outage probability and out coverage that you have calculated. Now probability of error can also be calculated for selection combining. For selection combining probability of error by using Q function, that can also be computed, but that is a real hectic analysis. I will write the equation. If you want me to derive, I will derive. That's not a problem. Okay. Over AWGN channel, let's say over AWGN channel, because for relay it will shift again. Probability of error for AWGN over AWGN channel for selection combining can be written in terms of Q function square root of 2 into gamma B. Okay. Now that is gamma is equal to hi square into gamma bar. Now it is not constant. This gamma B is fluctuating. So probability, now this is fluctuating. This is what I mean. This is fluctuating. So probability of error or PB bar, that is equal to 0 to infinity 1 by 2 into e to the power of minus gamma into PDF, that is P gamma D gamma. This will result in some equation m by 2 summation I is equal to 0 to m minus 1 minus 1 to the power of m into m minus 1 choose m minus 1 choose m divided by 1 plus m plus gamma. This can also be derived. Okay. Don't be under any impression that this cannot be derived. This can be derived. This can be easily derived. But you need a little bit of analysis of just concentrate on this analysis today. I will try to show you in the next class, because if you consider a DPSK or something like that, to derive this, you need little bit of mathematics. Okay, little bit of mathematics like PDF and selection combining for relay and for AWGN. So this is little bit, okay, little bit of what do you call binomial distribution and little bit of selection combining ideas are required. You just try to analyze what has happened here at equation A, B, and C today. Okay, this I will derive, but I'll give you a hint of how to derive. First, PDF of selection combining using Rayleigh you have to find out. Okay, RAWGN. You can choose Rayleigh also, because exponential of hi square becomes equal to 1. You can choose Rayleigh also. Okay. Now, if you choose Rayleigh, what happens? PB is equal to 0 to infinity 1 by 2 e to the power of minus gamma into P gamma. That remains the same. Okay. Probability of this. Okay. Don't be under an impression that this whatever is this Q of square root of 2 gamma B will come for AWGN. This is for Rayleigh. This is for Rayleigh. And for Raishan also you will have one more parameter. For Nakagami also you have the same. For this equation is for Rayleigh. Okay, this is for Rayleigh channel. So this probability of error in AWGN is Q of square root of 2 into gamma B. If you want it for this, you can use a Chernoff bound. Use a Chernoff bound, e to the power of minus x square by 2. Integrate between 0 to infinity, you will get for AWGN. Not so difficult, but you need to brush up your digital communication. But I'll give you a hint of how to solve this. First, you have to choose P gamma in such a way that P gamma of gamma is equal to m by gamma bar. That is 1 minus e to the power of minus gamma by gamma bar into m minus 1 into e to the power of minus gamma by gamma bar. This is the same equation what we have followed earlier. This is the same equation. Okay. So in this equation, what happens? BER of what constellation point you want? What is the order you want? M is equal to 2 for BPSK. M is equal to 4 for QPSK. If you want to go for DPSK also, you can do. For DPSK, I think in Andrea Goldsmith, it has been given for this equation, m by 2 summation I is equal to 0 to m minus 1 to the power of m minus 1 choose m 1 by divided by 1 plus n plus gamma bar. So how to do that? So from this equation, what you have to do is BER of DPSK with selection combining Rayleigh PDF is to be understood. How do you understand? If I remember and if I write it properly, PB bar or PE is equal to 0 to infinity 1 by 2 e to the power of minus gamma into P gamma of gamma D gamma. Now look at this. Now you know this P gamma of D gamma. Bring it over here. Bring it over here. Substitute 1 and 2. So the expression becomes 1 by 2 e to the power of minus gamma into this function, into this, correct? Now, once you obtain this, you have to integrate using binomial distribution. Previously, what I had done, no, same procedure you have to follow. M by 2 gamma, you bring it out, 0 to infinity e to the power of minus gamma. This minus gamma by gamma bar, you take it out into 1 minus e to the power minus gamma by gamma bar whole to the power of m minus 1 into d gamma. Using binomial distribution, you have to separate it out. You just try, otherwise I'll show you how to do it. There are one more important aspect is binomial distribution. You have to remember a plus b whole to the power of m is equal to k equal to 0 to m, a into m minus k to the power of m minus k into b to the power of k. If you remember that, you can derive this. So why are we doing all these things? What is the use of doing all these things? There are two important aspects that you can conclude. Two aspects you can draw from this. Two conclusions. First conclusion is outage probability of Rayleigh using SC. Outage probability of selection combining over Rayleigh channel. Now, what is the outage probability? This is P out or P naught in terms of 10 to the power of 0, 10 to the power of minus 1, 10 to the power of minus 2, so on and so forth up to 10 to the power of minus 5. This is my 10 log 10 or SNR, 10 log 10 gamma by gamma naught or SNR in dB. I will write 0, 5, 10, 15, 20, 25, 30, and let's say this is 40. Now, here, if I write something like this, outage probability for a selection combining without any diversity, what is the outage probability? Outage probability will be somewhere like this. In order to get a outage of 10 to the power of minus 5, in order to reach that outage of 10 to the power of minus 5, I need SNR of 40 dB. This is with m is equal to 1. Now the moment if I shift m is equal to 1 to m is equal to 2, I'll show you how it can be improved. Okay, you will get somewhere around, see this difference, 20 dB. The power you can reduce, how much power you can reduce. Now from m is equal to 2 to m is equal to 3, if you go again, you will get somewhere around 12 dB. Oh, sorry. You will get somewhere around 12 dB. This is for m is equal to 3, m is equal to 2. Now, if you bring in the notion of m is equal to 4, 2 cross 4 or 4 cross 4 or 1 cross 4, somewhere around m is equal to 4, you will get at 7 dB, m is equal to 4. This is even better than your AWGN channel. Now, this is one way of analyzing this. No significant idea you have got. I'll tell you the probability of error. Now, with the probability of error, if I write ABER on the y-axis and SNR on the x-axis. Now, I can say 10 to the power of 0, 10 to the power of 0, 10 to the power of minus 1 and 10 to the power of minus 5, similar to outage here at, let's say this is 30 dB and this is 20 dB, this is 15 dB, this is 10 dB and this is 5 dB and this is 0. If I don't use any branch, let's say m is equal to 1, simply I'll get an error flow, something like this. M is equal to 2, I'll get somewhere here at 20 or 24 or 25 for selection combining. Hey, how do you say that? If somebody asks, how do you justify your statement? You can justify. Look at this. Now, let's take a simple example. You will understand everything with this example. Assume 4-branch diversity. 4-branch diversity. 4-branch diversity is used. Each branch receives an independent relay fading signal. Okay, that is the idea. Each branch receives relay faded IID, independent and identically distributed Gaussian random variable with average SNR as 20 dB. Okay. Now determine the probability of error. Find out the probability of error that SNR will drop down to 10 dB. When does this SNR drop down to 10 dB? Okay, I'll write it as gamma as 10 dB. That is SNR. Okay, you can write it as SNR or whatever. Okay, determine the probability of error. I need to find the probability of error for SNR less than 10 dB and compare this with no diversity scheme. No diversity. This is the question. What is the question? I have a 4-branch diversity which is used where each branch receives an independent relay fading signal. If the average SNR is 20 dB and find the probability of error such that gamma is fixed at 10 dB or less with no diversity and with 4 diversity, order 4. What is asking? Without diversity, what is happening? With diversity, what is happening? Now that's what I told you. No? M is equal to 1. What is happening? Error flowed. Why do I have to believe you? It's a fairly logical question. If you say M is equal to 4, you are saying something like you can reduce the bit error rate. Okay, fine. Now, first you have to understand what is the power ratio. Power ratio is gamma by gamma I. Gamma by gamma I is what? 10 by 100, that is equal to 0.1. 20 dB. Okay, 10 by 100. Gamma by gamma I, that is 10 by 100, that is 0.1. Now what is gamma? Gamma is 10. What is your capital gamma or gamma average? Gamma average is 20 dB. Okay, what is how many number of branches you have to compare? B is equal to 4. First we have another branch with no diversity branch is equal to 1. Now what is the equation that I have? 1 minus e to the power of minus gamma by gamma threshold. Now first I will calculate it for P1, means 1 branch with a fixed SNR. That is 1 minus e to the power of minus 0.1 whole to the power of, that is what, 10 by 100, that is what I have done here, minus gamma by gamma bar. Minus gamma by gamma bar I have done, e to the power of minus 0.1, that is whole to the power of no diversity. 1 minus e to the power of minus 0.1 whole to the power of 1. What happens? Probability 1 minus e to the power of minus 0.1 means 0.095. Okay, 0.095. At what SNR? At this SNR. Now, I'll go with 4. The same SNR, fixed SNR. 1 minus e to the power of minus 0.1 whole to the power of m. M is what? 4. What is happening here? M is 0.00082. 8.2 10 to the power of minus 5. Okay. Now 10 to the power minus 4. Okay. Now what is happening here? Simply by adding 4 branches, this 10 to the power of minus 1, 10 to the power of minus 2, 10 to the power of minus 3, 10 to the power of minus 4, whatever it is, by fixing 5 and 10. Okay. The maximum SNR is 20 dB somewhere here. Now average SNR is 20 dB and what I have got here is at 10 dB of SNR without diversity, I have got something like 0.095. How do I write 0.045? Somewhere here, 9.5 10 to the power of minus 2. Let's say 10 to the power of minus 2. Now I will get a curve like this. Now by simply increasing m from 1 to m is equal to 4, what I have got? At the same SNR, by introducing some value of 4 or whatever it is, some value, m is equal to 1, 2, 3, 4, whatever it is, m is equal to 4, by adding more diversity branches, what I have obtained? This is somewhere here. Now look at this level, You simply can't get this error rate for m is equal to 1. M is equal to 2, maybe somewhere here. substitute in this equation, m is equal to 2, you will get another value. Now, what does it mean? It means you have found out CDF, you have found out PDF. From the PDF, you have found out the probability of error. The probability of error for a Rayleigh distribution is 1 minus e to the power of minus whatever, e to the power minus gamma by gamma bar you have written. Without diversity, SNR drops below the specified threshold with a probability 3 orders of magnitude greater compared to 4 branch diversity. Isn't it so? Now, this is the significance what you can infer from the probability of error, outage probability, and these equations. So for a selection combining itself, if you find out the probability of error 1 minus e to the power of minus gamma by gamma threshold, from this equation, if you simply find out what is happening with the probability of error, you will get this. Is this the best possible way? Is this the maximum diversity gain or the residual diversity gain that you can obtain from combining? No, there are other methods which will give you better than this selection combining that can also be understood in the later sections or later chapters. Now, let's go back to the question what he has asked. What happens if there is a delay? Now, if there is a delay, what happens is, because the bits are lost, let's say delay is a buffer and burst delay. That is the general delay what we see in case of most of the systems. Okay, buffer and burst delay. Sometimes it is visible, sometimes it is not visible. Buffer and burst delay. If there is a delay and then it reaches a certain error floor, the bit error rate, even with the increasing value of m is equal to 4, it reaches a certain error floor which is always higher in the order of magnitude, or which is always higher compared to m is equal to 4 or m is equal to 3 or m is equal to 2, whatever it is. Now, based on the branch, whatever you have set, your delay will be high. Means the delay, the probability of getting the error will be high. Now, if you talk in terms of SNR, you require higher SNR if you have a delay. Now, the error floor is reached at a fairly lesser error itself. Means every 2 bits in every 100 bits that you have transmitted will be in error compared to every 4 bits in every 1 bit or every 2 bits in 10 to the power of 4 bits that you have transmitted. So you can explain this in another way. When you have a delay, your ABR is stagnant. When you have a delay, your ABR is said to be stagnant. Means you will attain a error floor at fairly higher SNR and fairly lower BR compared to lower BR means the bit error rate, the error rate at a fairly lower bit error rate compared to the system which operates at higher M value. Okay, this is what your selection combining does. What have you understood in this class? Little bit of work is required in selection combining. Selection combining does, it selects the highest possible SNR from all the branches. It selects the average of the SNR from highest average from the threshold what it has been set. And the argument y square has to be maximized. That's why it has shown it as I conjugate is equal to argument max of hi square. So expectation, you take expectation operator, and then for a Rayleigh distribution, 1 by gamma bar e to the power minus gamma bar by gamma bar is the PDF, and then expectation of hi square you take, you just integrate, you will get the outage probability in terms of 0 to gamma threshold. This is the probability that the signal falls below the threshold, that is 1 minus e to the power of minus gamma threshold by gamma bar. Similarly, you have understood what happens with a single P out, the outage probability and the fading margin, what is happening with the outage probability and the threshold, and average SNR with the threshold. So outage probability with the selection combining of all branches you have calculated. So with respect to the probability of error, if they calculate the probability of error, you can calculate by using the same equation 1 minus e to the power of minus gamma by gamma bar threshold. With respect to the power ratio, you have to calculate because gamma average has been given and gamma I value has been given. So you can calculate the ABER based on whatever the probability of error or the outage probability, whatever they ask. Okay. Anything? Any questions at this point?
Yes, sir. I have.
Yeah.
Sir, the probability of error we calculate from these mathematical equations, and the probability of error I get from taking manual observations from the system itself.
While doing the hardware realization, yes.
Yes, sir. So how much how these two values deviate from each other?
Okay. You are talking about how much is the similarity between. Okay, that is your question, right? How much is the similarity with respect to analytical and mathematical?
Yes, sir.
Analytical and proved results. That is the question, right?
Yes, sir.
Now, this is a very interesting question actually. It's very difficult to answer this question, but I have a solution because in your software defined radios, first you have to estimate the channel. When you estimate the channel, what happens? You will get probability mass function, or your CDF you will get. Once you get the CDF, what happens? You will get the PDF. Now, based on the estimated value of CDF, you will curve fit it back. Now, you will assume a distribution which is near equal distribution you will get. Now I'll show you once again. I think my screen is visible. Okay. Now that is why this Chernoff bound and union bounds are available for that. Okay. Now ABER versus SNR. ABR versus SNR you have. Now let's say my mathematical upper bound is something like this. This is my mathematical analytical approach. By analytical approach, I have obtained a probability of outage or ABE or whatever. Now I have obtained somewhere at, let's say, 30 dB. 30 dB, that is my 10 to the power of minus 5. Now, with practical scenarios, you cannot simply say that you will get the same Monte Carlo simulations. You may get a little lesser value or little more value. Now, how much more, how much less? That is your question. Now, how much more, how much less depends on how many pilot symbols that you have trained. 10 to the power of 5, 10 to the power of 6, or 10 to the power of 7. If it is less than 10 to the power of 4 symbols that have been transmitted to fit a curve or fit a distribution, then what happens? No, your upper bound will be loose upper bound. Somewhere at 10 to the power of minus 2, you will catch up. But approximately it will match for higher SNRs. Now, if you use 10 to the power of 6, somewhere at lower SNR, let's say this is my 10 dB SNR, you will have Monte Carlo simulations matching with your preferred simulations. Nowhere in this world you will get a mathematical upper bound and a theoretical upper bound unless if you have a higher SNR greater than 20 dB. You will have a hard solution, means a soft solution which matches with your analytical approach. Otherwise, you will have some error. This error is accepted because you will come to know the behavior of the system based on the analytical approach. Now, the problem is if it goes above, if your Monte Carlo simulations goes above this, then it's a problem. Otherwise, it's not a problem because whatever maximum you have obtained through red line, it's the maximum. It is the maximum ABR that has been obtained for a particular branch. Now, if you are using Monte Carlo simulation, if you get better results than that, it's fine, absolutely fine. But this is the maximum result. And as I told you, if it goes, your Monte Carlo simulation results, if it goes out of this window, out of this red line, then that analytical approach, what you have done, maybe a little bit, it has to be reconfigured. Now, what is the exact SNR? That is your question. The exact SNR from 0 to 10 dB, if you take the interval from 0 to 10 dB, it will be on the order of 2 to 3 dB difference you will obtain. Okay, 2 to 3 dB difference obtained. From lower SNR, 0 to 10 dB lower SNR, you will have a separation gap of 2 to 3 dB. That is quite acceptable. That is quite acceptable because you're getting a better performance. You will get a better performance because in Monte Carlo simulations, depending on the distribution, you will run it for many number of iterations. That is accepted. But if it goes out, then you have your simulations. Then your simulations are wrong or your analytical approach is wrong. Okay, just go through this video again because you may not be familiarized with your binomial expansion, binomial series, probability of outage or probability of error, so on and so forth. Just go through this once again, and if you have any clarifications, do let me know. I'll derive the probability of error analysis for your DPSK system or a relay fading channel if you need it in the next class. Okay. And we'll try to solve some more problems to understand how the ABER will vary. And then I'll go for the conversion analysis. Yeah, Yuvraj.
Sir, can you go back to the optimized selection combining thing? What was the name? I forget.
Switch and stay. Switch and stay.
Switch and stay. Yes.
Yeah.
So correct me if I'm wrong, but the idea here is that you select a channel and you don't think about switching until and unless the channel you're on, its SNR reaches below gamma TH. That's what's happening.
Exactly.
So, sir, then in the starting, when I'm referring to the figure, you take the pink line from the starting, and then as your peak comes down and you hit gamma TH, why don't we directly transition to the green one?
Here,
why go to the yellow
this
one?
point?
No, sir, the point that's below. Basically, you're going to stay on the black line until it goes below gamma TH, right?
Exactly.
So at that point, when it first goes below gamma TH, why do we not shift to the green curve? Why yellow?
Green is available. No, green is available. This one, no, you are talking about this one. This one, right?
The previous crossover, sir, not this one. Below.
Which crossover? This is one. This is two.
One.
Here.
And
okay. Now look at this. Now this is the legitimate question. Now look at this. There is a SNR, which is this SNR point is not less than the threshold rate. Now you are going to this point. Now you don't have any other alternative. That is why you are switching over here or to this point, any point. That's immaterial. That's not a problem. Now, because I have written the figure here, you are under an assumption that the green one looks similar or looks higher than the threshold. But while combining, no, automatically the switch combines only if this goes below the threshold. Now, let's say I understood your question. Now, at this point, what happens? At point 1, what happens? You have a fairly good SNR. Now, if you follow this blue line, what happens? You might reach a lower threshold value. That is your question. Now, why do you want to switch here? You can switch here. That is possible. In order to avoid those consecutive switches, I have written it like this. You can write that. There's no harm done. You can write that. Now, the crux of the problem in switch and stay combining is, as long as you have gamma threshold in your control, just don't switch. If it is going below the gamma threshold, if you have any other alternative branch which is available at that particular instant while following the same branch, if you have any other alternative approach which can give you a better SNR, switch it. That's all. Okay.
Okay, sir. But I'm still confused in the sense that I understand when to switch.
Yeah, okay, because sir. I might have written wrong here. While switching it. I'll write it to you in the next class. Like, I'll take some 3-4 branches and I'll switch it over based on the switch and stay. Okay.
So, sir, in the end, when we do decide to switch, the algorithm is same. Whatever you have available, maximum SNR that's above threshold, you select that.
Correct.
That's it.
Correct. That's all.
Yeah.
Now, if there is no other alternative for the SNR, then you have to follow it. Follow the least possible SNR. If there are no other branches which will give you higher SNR greater than the threshold, then you have to stay in the same combined branch all the time. Okay, unless if you get a higher SNR value. Okay.
Yes, sir.
Fantastic. Yes, I think you have assignment at 11:30. You please go ahead and 1 second. I'll take attendance. 1 second. I'll take attendance. Okay, then yes, I've taken the attendance and you can go ahead for the assignment. And if you have, just go through that probability, outage probability and probability of error once again, and look at the binomial expansion, how it has been done, and then get back to me if you have any clarifications. Okay. Fine, then you can leave the meeting, and then we'll do it in the next class. We'll take another selection combining scheme, and we'll try to concentrate more on the problematic solutions. Okay. Okay then.
Sir,
Thank you, sir.
Thank you, sir.
Assignment will be posted.
What happened? What happened?
On the tool, sir.
Hello? What happened?
Sir, the assignment will be posted on the respective section teams, right?
Section. Yes.
Thanks.
Yeah.
Thank you, sir.
Cool. Bye-bye.
Thank you, sir.